The last thing we're doing in 4.1 is we're talking about inflection points, and we're going to talk about them with respect to f, with respect to f prime, and then obviously with respect to f double prime. Inflection points, by definition, are where are the points where your function, your graph, changes concavity. So it either goes from concave up to down, or vice versa, down to concave up. So when we are looking for possible inflection points, here are the steps that we're going to take. One is we are going to look for where our second derivative is either 0 or undefined. All of those points are possible. Oh, look, I even have it highlighted. Possible inflection points. So we're going to look for those points first. So we're going to take, if our graph is f, we're going to take f prime and then take its derivative, f double prime. We're going to locate those zeros algebraically. Second is similar to what we did in our first derivative test, is we're going to use a number line to determine if those points are in fact inflection points. So critical points always have a derivative that's equal to 0 or undefined. But a point that has a derivative of 0 or undefined is not always a critical point. That's that square, rectangle, rectangle, square. Now the same thing holds true for inflection points. Inflection points always have a second derivative that's either 0 or undefined, but because the second derivative is 0 or undefined does not necessarily determine that it's an inflection point. So let's do an example. And let's see how this looks first algebraically and then with respect to the derivative graph. So if I have this question and they're asking me to use the second derivative to find all of these inflection points, I'm going to first take f prime and then f double prime. And there's our f double prime. We want to see where this is either 0 or undefined. It's not going to be undefined, but we know that it's going to be 0 when x is 2. So now we're going to look at our number line with respect to f double prime, folks, with respect to f double prime to see if at that point x equals 2, if to the left and to the right of 2, it goes from positive to negative or vice versa. So we pick a number that's smaller than, we pick a number that's smaller than 2. How about 0? And we evaluate f double prime of 0, and we get a negative number. And because we know that's negative, so f double prime is negative to the left of 2. I'm going to choose 3 for the value to the right of 2. And I get that f double prime of 3 is 2. More specifically, it's positive. So I know that x equals 2 is an inflection point because f double prime changes signs. Now what I love about this is we've already done this, so it's just going to drive it home. We did this in chapter 2. So inflection points with respect to the derivative graph. If I have a function f, and I know that f double prime changes signs at some a value, then I can say with certainty that f has an inflection point at x equals a, and on the derivative graph, that's where f prime is going to have either a local min or a local max. So folks, that's another way of saying when f prime goes from increasing to decreasing or vice versa, I have an inflection point. So if our derivative graph has a local max or a local min, there is an inflection point there. If our derivative graph, another way of saying it, goes from increasing to decreasing or decreasing to increasing, same thing as saying a local min or a local max, there is an inflection point at that point. So we're going to do an example of this. All right, here's a little throwback, folks. So here is the same graph that we worked with in the first part of this section where they wanted us to find any local mins and maxes. Boom. fine, we did that. Now it's asking us to find all of the x coordinates for the inflection points to f. Keeping in mind, this is f prime. This graph is f prime. So I want you to relate all of that information to f prime. What is f prime telling me? And remember, if I'm looking for inflection points, I know that f prime is going to be a graph that's going from decreasing to increasing or vice versa. So let's see. Those are the local mins and maxes, folks. So here I can see my graph is decreasing. And then right here, it increases. So I know that at -1, my graph went from decreasing to increasing. That's going to be an inflection point. So I can tell them right now at -1. Oh, what a mess. Then where else on that graph would we identify that our derivative goes from decreasing to increasing or vice versa? And I'm hoping that you saw that that's at -1, 1, and 3. What's our reasoning? Our reasoning is because our derivative graph goes from decreasing to increasing at -1 and 3, and then increasing to decreasing at x equals 1. When you are given information about the derivative graph, you have to explain your reasoning using the derivative graph. You can't say it's because f changes concavity at those points. You need to specify what's going on with the derivative. Now let's look at that second question. And I put that information there. I'm going to add a little bit of information in a second. That second piece, which we've seen before, is asking us over what interval from -3 to 4 is our graph both concave down and decreasing relative to f, the graph of f, concave down and decreasing. And remember, I want to justify this with f prime because that's what's provided. So you'll see in red that these are the things that happen when my graph is concave down. And you notice that with f, it's just a shape. F prime is decreasing, f double prime is going to be negative. And relative to your function decreasing, well, f is just going to be dipping, if I'm reading it from left to right. F prime is going to be negative, and nothing is relevant with f double prime with respect to a function decreasing. So we are looking for, on this graph, these two conditions occurring simultaneously. So this is another way of saying, where is that derivative graph decreasing and negative? Where is that derivative graph decreasing and negative? So I'm looking here, and that graph is decreasing here, but that's positive. So right here, our derivative graph is decreasing and it's negative. So we know that's one interval. And where's the second interval? There's my second interval. And our explanation for this is that our f prime is decreasing and negative over those two intervals. Since I have you as my captive audience for a minute, let's just look at this graph of f prime, and let's tease out whatever information we can from this graph. So here is the one thing I know. Over this interval, from, let's at least say -5 to -2, my function, my derivative graph, is decreasing and positive. What do you think that tells me about f? My derivative is decreasing and positive. What we do know is that if f prime is decreasing, I know f is concave down. If f prime is positive, I know my f is increasing. So I know that the shape of f over that interval from -5 or whatever to -2, that f graph is going to be concave down and it's going to be increasing. And I'm hoping that you see that it's going to be concave down not just from -5 to -2, but it's going to be concave down from -5 all the way to, I think that's all the way to 1. It's going to be concave down. And then what happens at 1? That's a local min, right? That's where our derivative goes from decreasing to increasing. So I know there's an inflection point at x equals 1. I have an inflection point. Great. And then what happens from 1 to 6? Let's look. Well, f prime over that interval from 1, oh, here, let me just break it down from 1 to 4. Over that interval from 1 to 4, let's see what f prime is doing. F prime is increasing. F prime is increasing and it's negative. So that tells me that f is concave up and decreasing over that interval from 1 to 4. And then the last thing we could say, I'm not going to write it down, is from 4 to 6. F prime is increasing and it's positive. So I know that my f graph would still be concave up, but now increasing. So if we took that information, what we're saying is right here over that interval from -4 to -2, our f had to have been concave down and increasing. And we can see it right there. Concave down, but increasing. And then we identified -2 to 1, still concave down, it's decreasing, right? But now it's decreasing since our derivative is negative up until 1. And then at 1, switch, we've got an inflection point, right? And then we identified that from that interval from 1 to 4, my function is now, my derivative is increasing, but it was still negative, right? So my f graph is still decreasing, but now it's concave up. And then that last little stretch was increasing and positive, which told me that my f graph was concave up and increasing. I'd like you to try some of these problems and see if they make sense to you. I'm going to write down the answers just so that we can walk through them. You'll notice that question 1 is showing you a graph of position, where problem 2 is showing you the velocity graph. So if we looked at question 1, they're asking, when is P moving to the left? And we would say that's where our position graph is negative, or sorry, where it's decreasing. And we know that it's decreasing over that interval from 0 to 1 and 4 to 6. Standing still, my position is going to be plateauing. First time it reverses directions, clear, x equals 1. And it's moving at its greatest speed. That's where I'm looking at the slopes. I'm looking at the derivative of that, and I'm just looking to see which one is, which slope is the greatest. And it looks like from 4 to 6 is the greatest slope overall. So now we're shifting gears, velocity, and we're looking at this graph now as the velocity. So let's try that. So if we're looking at question 2 now, when it's asking when is P moving to the left, I'm now looking for where is my velocity negative. This is the velocity graph, so I'm looking for where that value is negative, and that's from 1 to 4 over the interval. It's standing still when our velocity is 0, and that occurs at those 2 points, 1 and 4. Right? So that is really where P stands still, the only 2 points. And it reverses direction at x equals 1 because our velocity changes from positive to negative there the first time. And then when is it moving at its greatest speed? Remember, the y values here are our speed, and so that would be right there when x is 6. So I want you to take a second to look at 3, see what you think your solutions are going to be. Pause it, let me know. So the first thing I do here is I just identify, I sometimes need my brain to just remember. Below is negative, above is positive. So if they're asking me, which of the following statements correctly describes f over that interval from -1 to 5, we would know that anytime that graph goes from negative to positive, that means that graph, f prime, goes from negative to positive, that means that f is going from decreasing to increasing. So negative to positive occurs at 0, and that's the only place. So I only have one local min if we're all in agreement. So I know that x equals 0. I know that x equals 0 is a local min because my graph goes from negative to positive. When my graph goes from positive to negative, that's a local max. Where on that derivative graph do we go from positive to negative? At x equals 2. So I have a max at x equals 2. And it didn't ask, but where are those inflection points? Remember, inflection points is where our derivative graph goes from increasing to decreasing or vice versa. So if I wanted to see inflection points, I would say there's definitely one at 1, at 3, and at 4. But our answer for 3 is C. So last thing is, if you're looking at question 4, they're giving us dy dx, so they're giving us our slope. It's implicit. And then they're also providing us with information that y is always larger than 1/2. And we've got this point that's on there, 5, 1. So which of those statements has to be true? Well, let's look at A. Does the graph of f have a 0 at P? No, because the y value is 1. So no. So B through D are referring to local mins, maxes, or undefined. So I'm going to use that derivative, and let's just see what happens when we plug in the 0.51. So we do end up with 0. So I know that that is a possible min or max, or neither. So what do? I'm going to use a number line and see what happens to the left and to the right. So I plugged in a value to the left of 5, that's 4, and all I know is x is 4. I don't know the corresponding y value, but remember, folks, we at least know that y has to be bigger than 1/2, which tells us that this denominator, regardless of what that y value, is, that denominator is positive. So I end up with 4 minus 5, a negative over a positive value. That's negative. So then let's choose a point to the right of 5. And we see the same scenario happening here, except now I have a positive number over some unknown, but we know it has to be positive, which means to the right of 5 is positive. So now I know that my derivative has gone from negative to positive, which tells me that my f of x has gone from decreasing to increasing. So I know that there is a local min at P.